Okay, in 4.6 we're going to be still solving quadratic equations, but we may run into the imaginary number, or the imaginary number with other numbers. So first we should talk about imaginary numbers. The imaginary number. So let's take all numbers, split them into two groups. We'll have the real numbers. Real numbers like 1, 3, 7/3, 5/12, the square root of 3, pi, all sorts of different numbers. All the numbers you've ever encountered have been real numbers. Now we have the imaginary ones. Okay, so the imaginary numbers are based off of a one particular number. It kind of gets the ball rolling. So the imaginary number is a number we name I, and it is the square root of -1. So why would we call the square root of -1 imaginary rather than real? What's so unthinkable about it? Well, let's think about what the square root of a number means. Just waiting for my computer to let me write a 1 here. There we go. Let's think of it in terms of a square root that we know, the square root of 9. The square root of 9 means a number that multiplies by itself and gives you 9. And since 3 times 3 times itself, is equal to 9, then 3 is that square root. And since -3 times -3 gives you the same thing, -3 times itself gives you a positive 9, then we include -3. Let's even think about the square root of 1. 1 times 1 equals 1. So 1. Also -1 times -1 equals 1. So you get positive and -1 are solutions to this. So they are square roots of 1. Now think about the square root of -1. What number times itself will give you a -1? 1 won't do it. 1 times 1 is 1. We just talked about that. And then if you think, well, let's involve a negative number. Let's do -1 times 1. That won't work because the square root means times itself. A number times itself. So you couldn't do square root, or you couldn't do -1 times +1, because that wouldn't be a number times itself. So if you use -1, you'd have to multiply it by -1 to fit the definition of a square root, and that's a positive 1. So this has no square root. It has no real number, at least. No number that we've ever encountered that you could multiply by itself to get a -1. So we just call it I and work with it from there. Okay. So that is what we call the imaginary unit. And this gives way to a whole new class of numbers that we call the complex numbers. Some examples of complex numbers are, let's say, 1 plus I. So we took a real number and we added an imaginary number, and we get a complex number. We could do 2 plus 3i. There's another one. 5 minus 6i. There's another one. The square root of 2 plus I times the square root of 7. That's another imaginary or a complex number. So an imaginary number or a complex number, I'm using these interchangeably. Many people do use them interchangeably. Is any number that looks like this: a plus b times I. So a is just a real number, and b is a real number that you multiply by I. So anything that looks like that is an imaginary number. Okay. Let's say we were to add two imaginary numbers together. If we added a plus bi plus c plus di, well, then we would add the real parts together. A and c are both real numbers, so just add a and c, and then we'll add b and d, and that'll be multiplied by I. It's like having common terms, like terms. bi and di are both like terms. So here's an example. 2 plus 3i, that's an imaginary number, plus 5 plus 7i, there's another imaginary number. We'll add them together. Add the 2 and the 5, that's 7. We got 3i here and 7i here. Just like if we had 3x plus 7x, we just have like terms. We'll add them together. We get 10i. Okay. And two imaginary numbers can only be equal if, this is if and only if, this is the only way that two imaginary numbers can be equal to each other. That's if a equals c, that is to say the real number equals the real number, and b equals d. The two coefficients of I are the same. Right, so we have what the imaginary number is, how to add them together, how to set them equal, what it means for them to be equal to each other. Now we'll run into them and work with them more in the sample problems. So I'll see you there.